Last few classes, we talked about partial differential equations. We talked about Laplace's equation. We talked about heat equation. We talked about wave equation. Today's class, I want to talk about a couple differential equations and how we might solve a couple differential equations numerically. So I pick the following example or the following illustration. So if you think about a carbon dioxide molecule, one way of thinking about that is several masses attached together by springs. So it's a coupled system of masses, and that's an example of the problem we'll solve today. Another example would be just say a building or a structure or a bridge. You can often think of that as an example of a coupled system of masses that are attached, connected by springs. And again, you would solve that with coupled differential equations. If you have an arrangement of masses where the masses are just attached to separate springs, then those masses will oscillate independently with some natural characteristic frequency, with some natural mode. If you have an arrangement of masses that are attached together with common springs, then the oscillations of those masses will have a number of natural modes in which the masses oscillate. So we're going to investigate that. In particular, in today's class, I want to look at a system involving two masses that are coupled together by springs, and we'll solve for the positions of the two masses as a function of time. So if you imagine these two masses, M1, M2, and they're connected by springs, we're going to solve for their positions x1, x2 as a function of time. So here's the specific case I was going to think about. I made a little sketch of it upstairs here. So I got this mass on the left, M1, mass on the right, M2. I've got three springs here. On the left, K1, in the center, K2, on the right, K3. The way I've arranged the situation is that this spring on the left its left-hand end is attached to this wall and is fixed. This spring on the right, its right-hand end is attached to the right-hand wall, and that's fixed. But the masses can obviously move to and fro. So I've called x1 the displacement of the mass on the left from its equilibrium point, and I've called x2 the displacement of the mass on the right from its equilibrium point. And with this arrangement, with this particular problem, I want to work to writing down the equations of motion that are describing the masses and solve the equations of motions describing the masses, noting that this is an example of a coupled system between these two masses. So to get us going, so I should note that in this particular example here, I've kind of imagined displacing the masses initially towards the right-hand side, and I'm going to release them. So when I displace them towards the right-hand side of this slide, I'm stretching the spring on the left here. And so it will exert a force towards the left on this first mass. So that's one force coming from the spring on the left. That's simple. Over here on the right, if I pull the masses towards the right, it's going to compress the spring on the right, so spring 3, And so spring 3 will exert a force on the right-hand mass. This should be K3, X2. It will exert a force on the right-hand mass towards the left. So those two situations are kind of simple because mass on the left, mass on the right is just exerting a force on the, spring on the left, spring on the right is just exerting a force on the mass on the left and mass on the right. A little bit more complicated is the spring in the center here. So it will exert equal and opposite forces on the masses on the left and right of it, and the size of the forces that are exerted on the masses to the two ends of that spring is determined by this little factor here, its spring constant, and the net stretch or compression of that spring. And so that's the situation for the third force. So understanding the individual forces, we could then write down Newton's second law for one of the first mass, say M1, and the sum of the forces that are acting on it. Write down Newton's second law for the second mass and sum up the forces that are acting on it. And in that way, we can build a couple differential equations that describe this problem. So that's all I'm doing on this slide, is turning that into words. So if I think about mass number 1, so this guy here on the left, the sum of the forces on it will determine its acceleration. And the two forces that are acting on it are the force due to the left-hand spring that only acts on mass 1, and then the force that's coupling the two masses. That this should be a K2 here. So that's the arrangement of forces on mass number 1, and if I add them up, I can pull out the common factors involving the position of mass 1 and the position of mass 2. I get this little arrangement here. Downstairs here, I did the same thing for mass 2. So I could add up the forces on it to determine the acceleration of mass 2, the right-hand mass. There's this force here that is due to this compressed spring, and that's only acting on the right-hand mass. And then I got the force that's due to the spring in the middle. Again, this should be K2, and that's given by this little expression here. So again, over on the far right, I pulled out the common factors of the position of mass number 1 and the position of mass number 2 in this expression. So these two equations amount to two coupled differential equations, two coupled second-order differential equations. So we've got differentials with respect to second-order differential with respect to x1 here, second-order differential with respect to x2 here, and then on the right-hand side of these equations, we've got both the x1s and the x2s. And so it's these right-hand sides that are coupling together the two differential equations that we're going to go ahead and solve numerically. There is a handy way of denoting these coupled differential equations. That is especially handy if you have other cases. So you could imagine having not 2 masses and 3 springs, but you could imagine having 3 masses and 4 springs, or 4 masses and 5 springs, so on and so forth. So you can write this particular case out of the 2 masses and 3 springs in a manner using matrices and vectors that kind of will make the generalization to n masses and n+1 springs kind of clear cut and kind of obvious. So I just wanted to show you that. So how do we write these two coupled equations as a matrix equation? Well, here's the matrix equation downstairs here on the on the bottom left. In this equation, you see the second order differential with respect to x coordinates. So that's the x double dot. You see the x coordinates themselves, that's the x. The m and the k are the mass matrix and the spring constant matrix. And the x is a column vector that contains the two positions of the two masses. So if you were to think about writing this out as in terms of the matrices and the vectors, if you take the vector x and multiply the upper row of the spring matrix, you're going to get the first of these differential equations, the one that's for the left-hand mass. If you take this column vector x and you multiply the spring matrix, multiply the bottom row of the spring matrix, then you're going to get the second of these differential equations for the second, the right-hand mass. So these two equations are embedded in this little vector matrix equation. So that's a handy way of writing it. Okay. So I want to start looking at the solutions to those coupled equations analytically, first of all, and then we're going to look at them numerically. When I look at them analytically, I'm just going to pick out what we call the normal modes of the masses in this situation. And in the normal modes, the masses oscillate just rather simply sinusoidally at some common frequency. And we're going to discover that there are actually two normal modes of this two-mass free spring system that have these simple sinusoidal oscillations of the masses at a common frequency for the two masses. So I'm going to try and just sort of pick out the solutions that correspond to those normal modes. Now, those are special modes that we can find analytically fairly straightforwardly. With a numerical solution, we'll be able to explore the kind of the full space of the oscillations. So not just the normal modes, but all sorts of other modes of oscillations of the masses. Okay. So here's a couple of differential equations again in this this particular matrix and vector notation. And I'm just going to make a hypothesis, and we're going to start with that hypothesis, and it's going to lead us to these normal modes. I'm going to make the hypothesis that there are solutions to these coupled differential equations in which the positions of the masses x1 and x2 oscillate sinusoidally with some common frequency. So I'm going to make that hypothesis, and I'm going to take that hypothesis, write out that solution that's a hypothesis, and then plug it into the coupled differential equations and try and learn something about the frequencies based on that. Okay, so the idea is that our x1 and x2 could either be sine waves or cosine wave functions, or equivalently, it's more convenient to write them in terms of complex exponentials. These functions here, this should be e to the minus I omega t. And so the hypothesis I want to follow up on is that this quantity x, this column vector, which has these two components for the two masses, has a form that looks like this. So e to the I omega t, that's encapsulating the sinusoidal oscillations. And then the alpha 1 and alpha 2 are just two complex numbers that are determining the amplitude of the oscillations. And I can write that in this little form here. So now alpha is this little column vector of the amplitudes of these oscillations, and the sinusoidal nature of the oscillations is built into this complex exponential. So I'm just going to substitute this hypothesis that the sinusoidal oscillations at a common frequency. I'm going to substitute that into this differential equation, or these coupled differential equations represented in this matrix form. And if I plug this expression for x into this coupled differential equations, right? When I differentiate the column vector x twice with respect to time, I'm just going to get a factor of minus omega squared, so I omega squared out of that differentiation. And so plugging in this hypothesis, I get this little expression over here. So on the left-hand side, I got this additional factor of minus omega squared that's come out of the differentiation. But the time dependencies on the left and right, they're going to be the same for the sinusoidal solution. And I'm just going to cancel those guys out. And if I do that, it basically leads to this little expression down here. And this expression, if I solve this expression, solve it for omega, it's going to tell me the normal modes of the oscillation. So what are the frequencies of those oscillations? Okay, so I want to solve this little expression here. And this looks like a kind of like an eigenvalue equation, or a generalized eigenvalue equation. And I can find the frequencies that solve this equation by just setting the determinant of this quantity in parentheses equal to 0. So finding the values of omega that solve this equation here that's come out of our coupled differential equation with our hypothesis is just equivalent to finding the values of omega, the characteristic frequencies that fulfill this equation, the determinant of this particular matrix here. So this is a matrix equals 0. So all I've got to do is calculate the determinant of this matrix, and that will enable me to solve for omegas. To keep this kind of simple and straightforward, I've made the masses the same masses, so M1 and M2 are the same. I made all the spring constants the same, so they're all equal to K. And then my matrix M just becomes this diagonal matrix. My matrix K becomes this sort of non-diagonal but symmetric matrix over here. And so if I form K minus omega squared times N, I get this matrix here. So this matrix here is K minus omega squared N, the spring matrix minus omega squared times the mass matrix. And if I take the determinant of that, so the product of the diagonal here and the off minus the product of the off diagonal, I get this little expression here. And if we solve this expression, this quadratic bit here, if we solve that for omega, there's two solutions for omega. There's this one here, so omega squared is K over M, and this one here, where omega squared is 3K over M. So these are the two solutions. These are the two frequencies at which we'll see oscillations at the normal modes, sinusoidal oscillations of the masses, and they're called the first and second normal modes. Okay, so this slide and the next slide, I'm just showing you pictures of these normal modes. So in this lower frequency normal mode, so this is the one where the frequency is simply actually the square root of the spring constant divided by the mass. The two masses will oscillate in phase to and fro about their equilibrium points. So if we imagine we got two masses here, we got spring between them, and we got springs on either sides attached to walls. if I displace the two masses towards the towards your left here, and then release them, these two masses will just swing backwards and forwards in phase like this. And this will be at that characteristic frequency as the square root of the spring constant divided by the mass. So that's kind of pictured upstairs here. I displaced the left-hand mass towards the right and the right-hand mass towards the right by the same amounts. And then when I release them, they're just going to oscillate with a, so this is a sinusoidal oscillation. It has a common frequency, and they're in phase with one another. When the one's towards the right, the other's towards the right. When one's towards the left, the other's towards the left, and so on. This is the expressions for their position as a function of time upstairs here. You see simple sinusoidal oscillations with a common amplitude, with a common frequency, and they're in phase with one another. Okay, so the other mode, is, so again, imagine I've got these two masses with the three springs, the spring here, spring over here, spring over here. The other normal mode where you see sinusoidal oscillations is if I displace the two masses, say by the same amount, but I push them together, or I would displace them by pulling them apart. So in this case, again, you get simple sinusoidal oscillations of the two masses. You'll get these oscillations at the same frequency, but now they're out of phase. They have the opposite phase. And so that's the second mode. That's at a frequency that is different from the first mode. So it corresponds to this square root of 3 times the spring constant divided by the mass. So it has a different frequency. So I pictured this here. I displaced the left-hand mass towards the right by an amount x1, but I've displaced the right-hand mass towards the left by an amount x1. And then I've released them, and this plot down here shows the position of the left-hand mass and the right-hand mass as a function of time. And so you see, again, right, you've got sinusoidal oscillations in both cases, so it's a normal mode. The two frequencies are the same, but the phases are opposite to one another. I tried to write down the expressions here, but this should have a plus pi in because it's out of phase. But the amplitudes are the same, the frequencies are the same, but it should be out of phase.